next part, let's briefly discuss if you had time to think about this. So do you know what is the order that any of these materials has, in particular, which symmetries its order breaks? You can choose, of course, any of the four. Yes, yeah, that's perfect. Wonderful. Any other? Which one? Sorry. Which symmetry? Sorry. Inversion symmetry. Yes, that's structural, of course. Yeah, that's also perfect. Then, any other thoughts? Any other material that breaks time reversal? Why does it break time reversal? So superconductors don't have to break time reversal. They can, of course, but they don't have to. Yeah, in the case of iron diselenides, I mean, of course, the superconducting state is not fully understood, but in principle, one can think that it doesn't break time reversal symmetry. Right? Any other thoughts about any of the four? Yes, it is magnetic, so it also breaks time reversal, right? But it also breaks inversion electronically. So nickel iodine is a multiferroic two-dimensional material. It has simultaneously magnetism and electric polarization. And any other thoughts? All right, good. This was already great. So we will, of course, talk about these four materials in the next few sessions. But yeah, the important thing for us to remember is that these different two-dimensional materials, they break each one of them different symmetries. And that is something that we can exploit for generating these different electronic states. All right, so in the last part of today's session, what we are going to do is we are going to have a very quick introduction to how the computational library works, so that you already know most of the things that you need for the afternoon session. So the basic idea is that the afternoon session is going to focus on running certain calculations using a Python library that is called Pycula, that essentially allows you to compute the electronic structure of two-dimensional materials using tie-bonding models. And you can include kinetic energy, spin orbit coupling effect, superconductivity, interactions, and compute different electronic properties such as electronic structure, density of states, local density of states, topological invariance, and so forth. And you can modify your Hamiltonian as you want. So the basic idea of the library is that it is developed so it is as easy to use as possible, in a sense that you can compute complex phenomena with a minimal amount of code, of lines of code. And then also something that is very important is that everything is compatible with everything. So you can add superconductivity and then spin orbit coupling, and then add interactions, and then compute the band structure, and then make a finite system, and then put defects and so forth. And you can do it in any order that you want. All right, good. So the library that we are going to use is this Pycula, that it is, as I mentioned, a Python library. And the basic idea is that for writing, let's say, complex models in a programming language, it is very fitting. Of course, in certain cases, one would like to do calculations without using an actual library, but by using a user interface. And for that, there's also a user interface that it's called Quantum Lattice, that we will not be using in the sessions, but I just want to let you know that it does exist if at some point you prefer to do calculations just by clicking buttons in a user interface. So for that, let me just quickly show how it works. So here you have 4 examples of how the user interface is done. So you essentially select which kind of libraries that you want, like triangular, honeycomb, square. You have different tests to the Hamiltonian, like superconductivity, spin orbit coupling, kinetic energy, or interactions, and then you compute electronic structures, density of states, local density of states, topological invariance, spectral functions in semi-infinite systems, and so forth. Everything that you can compute with this user interface, you can also do it with the library, but not all the functionalities of the library are in the user interface. So the library is much more flexible than the user interface, and that is why we are using it for the exercise sessions. All right, great. So now let me show you what is a minimal example of this library. And as a minimal example, let us just imagine that we want to compute what is the electronic structure of a Kagome lattice. So a Kagome lattice is this type of lattice. It's like a triangular lattice, but in which 1 every 4 atoms just disappeared. And this lattice is, of course, very important because it has flat bands. So if you want to write or compute this kind of model with spicula, the only thing that you have to do is first to create the geometry, and you just do it with geometry.kagome lattice. Then once you have the geometry, you can get the Hamiltonian. That gives you an object that it's a Hamiltonian. And then once you have the Hamiltonian, you can just compute the band structure with this method that it's get bands. And then you plot these K and E that are just 2 arrays, and you get this. So this is the basic idea. You can compute the electronic structure of a Kagome lattice just with 3 + 1 lines of code. And the basic idea is that all these different functionalities, they have many different keyword arguments, so arguments that are optional. And in that way, you can do, let's say, many different calculations. So for example, if you wanted to add first and second and third and fourth neighbor hopping to your model, you can just do it with a keyword argument here. All right. So the type of Hamiltonians that we are going to compute with this library are essentially of 2 types. And these 2 types are, of course, single particle Hamiltonians and many-body Hamiltonians. And the many-body Hamiltonians are going to be solved at the mean field level using the mean field techniques that we discussed before. So single particle Hamiltonians that we will consider have essentially this form. You may have a normal term, namely a term that has both creation operators and annihilation operators, and these are the different hoppings. Let me emphasize that these hoppings can be spin independent, they can be spin dependent, they can be spatially dependent, for example, short or long range, and so forth. So in this first term, you have effects like kinetic energy, strain, magnetism, spin orbit coupling, and so forth. Then another term that it's exactly solvable, that it's still quadratic, it's any superconducting term that can be solved with a Bogoliubov-de Gennes transformation that we will elaborate tomorrow. And the basic idea is that in the code, you can put any type of superconductivity that you want. It can be singlet, triplet, SPD, FG, wave, nodal, gapped, well, essentially anything. And then the electronic interactions that we are going to consider in the code are long-range Coulomb interactions. So any type of interaction that can be written as a density-density interaction. So let's say the simplest interaction that we are going to consider is local Hubbard interaction, which is interaction within the same site, but you can also have density with the first site, second site, third site, and so forth. Of course, all these interactions are going to be solved at the mean field level. All right, so essentially, for any calculation that you want to do, the workflow is more or less all the time the same. So first of all, you need to define what is the geometry of your model. So this can be, let's say, 2-dimensional system, 1-dimensional system. You may want to make supercells, add vacancies, let's say, add any kind of defect, and so forth. And the library has a special object that is the geometry object. That it's, for example, this G here. Then this geometry object can be transformed into a Hamiltonian object, for example, by this method. And this Hamiltonian object allows you to add many different terms to the Hamiltonian. So you can add strain, you can add more hoppings, you can add magnetism, you can add superconductivity, you can add interactions, and so forth. And once you have the Hamiltonian in the way you want, then you can compute the different properties of the Hamiltonian with bounded methods. And there are methods to compute the band structure, the density of states, spectral functions, topological invariants, and so forth. And I mean, you can also, let's say, extract the geometry from the Hamiltonian, and you can modify the Hamiltonians to go from two-dimensional systems to one-dimensional systems to zero-dimensional systems, and so forth. So what this means is that you are not, you can change the dimensionality of your system even after you define the Hamiltonian. Yeah, this is a very good question. If there's a way to visualize the structures from Picula. So in the exercise sessions, we are going to visualize these structures just by doing plots of the structure with matplotlib. If you want more fancy plots, you could do them with Mayavi. That's another Python library that you can use. And of course, if you use the user interface that was called Quantum Lattice, then in that one, you can see these fancy 3D plots automatically that essentially uses Mayavi for plotting the structures. Yeah, thanks for the question. That was a very good point. All right, good. And then maybe this is the most important point for today's session. Remember to install the library if you have not done it. And so you can get the latest version of the library just by writing this in your terminal. So pip install upgrade Picula, and this will essentially give you the latest version. So for example, if you install the library, let's say maybe a few months ago or weeks ago, you can just upgrade it to the latest version just by writing this down. And then, of course, if you wanted to install it not from PyPy, but just by linking your local Python to the library in your computer, you could also just download the full library by hand, just by git clone this repository. But this is the most convenient way of installing it, especially if you have Anaconda. All right, good. So now let me tell you a little bit about the different functionalities that the library has. And the first point to keep in mind is that we are not going to use all of them during the course. We are going just to use some of them. So especially electronic structures, density of states, and topological invariants. But I think that it's good to mention them so that you are aware of which kind of things one would be able to compute. So in particular, for single particle Hamiltonians, you can have both spinless, spinful systems with Nambu spinors. You can have both collinear and non-collinear formalism for mean field calculations, including superconductivity, and you can put any kind of constraint to the mean field. So you may want to do a mean field calculation in which you constrain the magnetism to be collinear and to have charge density wave and to have superconductivity, or you may want to quench the charge density wave and only allow for magnetism. Then, of course, you can compute electronic structure, density of states, and spectral functions for any type of Hamiltonian that you want. And you can also do, for example, electronic structure unfolding for supercells. So you take a supercell, you add an impurity, and then you want to see how the electronic structure of the, let's say, primal, the primal crystal was modified by this impurity. Then for interacting mean field Hamiltonians, as I mentioned, you can do essentially any type of mean field that involves density-density interactions with any constraint that you want. There are also functionalities to automatically identify the order parameter that mean field Hamiltonian has. We are not going to use them because I'm going to ask you explicitly to guess what is the mean field Hamiltonian or the symmetry breaking that you have, but the code has a functionality to automatically check all the symmetry breakings and tell you which one is the one that you have. And also there are some functionalities for mean field calculations with non-Hermitian Hamiltonians, but we are not going to use them. Then for topological characterization, one can compute both Berry faces, Berry curvatures, chair numbers, and Z2 invariants for symmetries with time reversal symmetry. Also, operator resolved chair number. So for example, if you want to compute a Bally chair number in a graphene system, you can do it also using a Green's function formalism for topological invariants. You can also compute topological invariants in real space. Namely, if you have a superstructure and you expect that the topological invariant is going to have one value here and a different value in other region, you can also do it in real space, also using Green's functions. And also you can compute topological invariant for amorphous systems. So even for systems that don't have translational symmetry. Then for spectral functions, you can essentially compute surface spectral functions for semi-infinite systems, for infinite systems, for systems that have single impurities in otherwise pristine systems, and any kind of spectral function. It can be the total spectral function or any operator resolved spectral function, like a spin resolved spectral function, value resolved spectral function, or any other operator that you may define. And all this done with a Green's function renormalization algorithm. And then if you are dealing with really, really large systems, namely systems that have maybe 100,000 sites or 1 million sites or 10 million sites, then you can perform some of the calculations using kernel polynomial algorithms. So what it's important to know about this kind of algorithm is that this is no longer diagonalization, but it's an algorithm that essentially relies on computing kind of spectral functions of your system. Anything that can be written as a spectral function, including density of states, for example, or momentum resolved spectral functions, can be computed with Chebyshev algorithms. But for example, you cannot do self-consistent calculations with this. So with this Chebyshev algorithm, you can go to up to 10 million atoms in a single core laptop without issues, and you can compute density of states, local density of states, momentum resolved spectral functions, and so forth. And the last thing is that the code also allows for doing different types of quantum transport. We are not going to use this again, but I just wanted to let you know about it. So in particular, you can do transport, of course, say metal-metal transport. The bimetal can be anything that it has a finite density of state, like a ferromagnet, a system with spin orbit coupling, or a topological insulator. You can also do transport between metals and superconductors. And bimetal, again, can be anything that has finite density of states, again, like a quantum spin Hall state, or a ferromagnet, or a conventional non-magnetic metal. And a superconductor can be any sort of superconductor, conventional, unconventional, breaking any symmetry, and so forth. And then all this is done with a non-equilibrium Green's functions formalism and S-matrix formalism. So in short, for doing transport, you need something that is metallic somewhere. You cannot do transport between superconductor and superconductor, for example, because in that case, you cannot use non-equilibrium Green's function with S-matrix. And then, I mean, one can also compute things like operator resolved transport. For example, if you want to compute spin conductance or valley conductance, and one can also compute things like the differential decay rate and different simulations of tunneling and contact STM. All right, good. So those were essentially the functionalities of the library. And as I mentioned before, you don't have to worry about that. You are not going to use many of them. All the ones that you will be using, you will see examples of them in the exercises. Then a couple technical notes about the library so that you are aware. So everything, or almost everything in the library, is a Python object, namely geometries, Hamiltonians, operators, potentials that you add to the Hamiltonians, and so forth. Namely that they are not just simple arrays, but they are objects that have bound methods and bound algebra. So for example, you can sum geometries, you can sum Hamiltonians explicitly, you can multiply operators explicitly, and so forth. So this is, of course, one of the motivations for using Python, because doing object-oriented programming is very easy in Python. Then in terms of performance, the critically computationally expensive parts of the library are written with just-in-time compilation numba. What this actually means is that effectively everything is written in Python, but at the execution time, there are some functions that are compiled with numba. In practice, this means that the code has a speed that is comparable to what one would get with C++ or Fortran. And then with regards to parallelization, the code has multi-core shared memory parallelization. This is not important for the calculations, again, but if you want, you can, of course, just switch on the parallelization. All right, great. So let me check how much time we have. All right, so in the last 10 minutes, let me walk you through a few minimal examples. So maybe one simple example is just a triangular lattice. This is very similar to the Kagome lattice that we looked before, but let me just reemphasize it so that you're aware of how this works. So again, what we have to do is first to get the triangular lattice, then once we have the geometry, we get the Hamiltonian. We get Hamiltonian, and then once we have the Hamiltonian, we get the band structure. And of course, this is the band structure of a triangular lattice. Now, if you wanted to add, for example, second neighbor hopping to the triangular lattice, the only thing that you would need to change is to add this keyword to the get Hamiltonian bound method. In particular, that it's Tij, and the first number is the first neighbor hopping. The second number is the second neighbor hopping. So by default, the code assumes that you only want first neighbor hopping equal to 1. But if you want to have first and second and third and fourth and fifth and so forth, you just have to add a list with all the hoppings that you want there. And everything works the same. So you get the bands exactly in the same way. The bands are now slightly different. So of course, this Hamiltonian that you have here essentially would realize this Hamiltonian. So a Hamiltonian in which you have T1 for first neighbors, T2 for second neighbors, and T1 is 1, T2 is 0.3. Then if you want to start adding other terms to the Hamiltonian, like for example, an exchange coupling or a Zeeman field, so a term like this one. So this is the kind of term that you can get, for example, by applying an in-plane field to the two-dimensional material that creates a spin splitting, or this is also the term that appears in ferromagnets intrinsically due to interactions. Then you can do this just with the bound method at exchange. And this bound method at exchange essentially takes as input either, let's say, an array or a function. If you give an array, it assumes that you want this type of magnetization. So a magnetization that has x component equal to 0, y component equal to 0, and z component equal to 0.5. If you had a system that had many sides and you wanted a magnetization that changes in space, the only thing that you have to do is to give a function, and that function will be evaluated in each point in space and added in that way. And then when you compute the band structure, you can color the states according to any operator that you wanted. There's, of course, a list of operators, but maybe one that is natural here is the SZ operator. So an operator that tells you who is spin up and who is spin down. So here, if you add an exchange field in the Z direction, then you see that you get a splitting between blue and red. So blue is spin down and up, spin up, and red is spin up. All right, good. So then another term that you can add to the Hamiltonian is, for example, spin orbit coupling, and in particular, Rashba spin orbit coupling. So this is the Rashba spin orbit coupling term. So this is the term that had a hopping and a spin flip that we had in the first break. So this term does not break term reversal symmetry, but it breaks the rotation symmetry in the spin sector. So originally, your Hamiltonian has SU2 symmetry coming from spin, but once you add spin orbit coupling, that symmetry is broken. And this is the term that appears, for example, once you put a two-dimensional material on a surface, for example, or this is the term that also some two-dimensional materials have intrinsically. So for example, Janus monolayers, which are transition metal bichalcogenides in which the chalcogen on top is different from the chalcogen in the bottom, they have a large Rashba spin orbit coupling by themselves. So if you want to add Rashba spin orbit coupling, you just say, well, add Rashba. And again, any kind of input for these terms in the Hamiltonian can be either a number or it can also be a function. So if you want a Rashba spin orbit coupling that changes in space, you just have to provide a function that changes in space. And
your bracket description for IJ is for nearest neighbor.
Yes, yeah, this is for nearest neighbor. So yeah, these brackets mean first nearest neighbor.
Before there were two second.
Yes, exactly, because this was second neighbor hopping, right? So here we had first neighbor hopping, second neighbor hopping. So yeah, usually one bracket is first, two brackets second, three brackets third. Yeah, thanks for the question. That was a very good point. All right, great. So now let's just imagine that one wants to add a new term to the Hamiltonian, like superconductivity, for example. So the superconducting term that we are going to consider first is this term that it's a spin singlet superconducting term. This is the simplest superconductivity that a system has. This is, let's say, superconductivity within the same site, different spins. S-wave spin singlet. So to add this term, then the term in the Hamiltonian is just add S-wave. And again, if you want to make it spatially non-uniform, or if you want the superconducting phase to wind in space, you could just give a function to this method as input. And when we have superconductivity, then we have a doubling of the degrees of freedom in our electronic structure. And this is something that we are going to discuss in detail tomorrow. But at this stage, let me just mention that if you have superconductivity, you can color your states according to the projection on the electron sector. And this is essentially what you see here. So superconductivity also opens a gap in the electronic structure. But now you have kind of a replica of your superconducting order, of your electronic dispersion. All right, great. So then for the afternoon, the only thing that you have to know now is that you have to download this Jupyter notebook from this address. And this is the very same address that appears in Team. So you can also either get the link from Team or get the link from here. And the basic idea of the Jupyter notebooks have examples with the code. So for example, this example shows how to compute the Fermi surface of graphene at different chemical potentials. And then you will have questions below. And these questions require you both to discuss with each other and also to modify the code. So you need to rewrite some statements in the code to do some new calculations to answer some of the questions. And then for the exercise sessions, what we are going to suggest is that you can do the exercises in pairs. So I mean, each one of you can have their own computer, but since many of these questions require you to discuss with each other, it would be very nice if you kind of sit in pairs and then you can discuss each point together. All right, good. So I think that this is everything for today's session.